Okay, I think we are ready to talk about the BIBO stability. Alright, so at first, the BIBO stability talk about bounded input and bounded output. Alright, in case you need to verify, is that this thing what I'm talking about is a digital BIBO stability. I'm not talking about analog. Alright, so if you're coming for analog, then I'll just suggest that you can leave this video now because we're talking about digital BIBO stability. So do not confuse digital to the analog. The analog BIBO stability I think is talking about final value theorem, while the digital one talk about summation of all your signals, which is a little bit more subtle. But anyway, let's just continue. So let's talk about the bounded input first. Your bounded input E, alright, if you think about it, your E comes from where? If you think about it, this is actually coming from back to here, this thing. Something that you're familiar with in the previous video, right? Your output is equals to your input multiplied by your transfer function, hk. Alright, so this is your input. So if your input is bounded, EL, so if L is equals to 1, 2, 3, blah blah blah, infinity. So what do I mean by all this? Okay, is that if I have E1 plus E2, alright, E2, then plus E3 all the way to E infinity. If I were to add up all this input, it must be smaller than m. Alright, it cannot go to infinity. It must be going towards some value and reach that value and stop there. Alright, so when it stop there and reach this particular what's that called? Value, alright, it must be lesser than infinity, but it's still some values that we can see lah. Alright, and therefore we can call this a bounded input. You see? Alright, so this is pretty a cool head start first. Next up is a little bit slightly hard to explain, but I'll just try my best, right? So your UK is equals to your EK multiplied by your HK, alright, input multiplied by transfer function is equals to output. Alright, so your output must be smaller or equals to your EL HK minus L blah blah blah. Right, you don't even know what the hell, right? It's coming back from our stuff, right? This thing, your EJ HK minus J. Instead of J, I just write as L. So this is what they write as L. So EL HK minus L. So if we come over here, is EL HK minus L also doable. So therefore over here, if alright, instead of this thing, or this is just a magnitude. So the magnitude of this must be I should say that the output must be smaller or equals to this magnitude. Okay, must be some bounded magnitude. Okay, but I haven't talked about bounded output yet because it's a very subtle one. But I just want to tell you that this is something of the meaning, your input and your transfer function mixed together. Alright, and when you goes from minus infinity to infinity now, alright, don't care about this sign. If I were to bring this thing and run it in terms of minus infinity to infinity, so in other words, your EL HK minus L, alright, if K is equals to 0 for example, and then this is from L is equals to minus infinity to L equals to infinity. Okay, so if L is it's 0 for example, let's start from 0 is E0, alright, HK, K is 0 also, so 0 minus, if L is 0, alright, let's start from 0, I'll have 0 minus 0 is E naught H naught, and that's all. Alright, and you can go on, but there's no meaning in there. Like if you say that, if you can say that if I have, maybe this is E naught H naught plus, alright, because we are talking about only K equals to 0, alright, so if K equals to 0, this is the K, right, this K is over here, alright, so let's continue. If L is 1, alright, so I have 1 plus, alright, K equals to 0, so I will have what? H0 minus 1, right? So I have this portion over here, I will have E1 H minus 1. This thing H minus 1 is talking about something that is not within the time domain, it's not within our causal system, right? Everything starts from 0. Any signal starts from zeros and it goes all the way. So anything before the 0 part, before all this part, Alright, we don't care. This is the time lah, okay? So any signal that comes before 0, because you wouldn't have any time that is minus, right? Because it's a causal system. Or I forget, is it non-causal or causal? But anyway, it's talking about only the positive side of the time. You wouldn't have any negative side. So this is why often this part over here is 0. Alright, just for your information only. Alright. But anyway, if you have this thing, alright, and then if you were to have 1k equals to 1, and you continue to do what I've just done just a minute ago, or in other words, if you want to know more about this, you can actually watch back this particular video, alright, on a causal and non-causal. I actually prove that to you also, but I'll not go into details on proving that once again, because I don't see that as a need. But anyway, let's just come back here. If I were to run this from infinity to minus infinity to infinity, from k equals to 0, k equals to 1, k equals to 2, all the way to k equals to infinity, alright, and then summation together with when L is equals to minus infinity to L is equals to infinity, alright. So it's a little bit subtle, but you kind of get what I mean. But anyway, the summation of all this thing must be smaller than infinity. Okay, so in other words, if I should bring this all the way out, I should say that it must be, or equals to, I should say that it must be smaller than infinity. Yeah, but to a more strictly speaking, if you think about it, your EL is your M, if it's equals to M, because EL, your input, can be smaller or equals to M, right? So if I were to sub in EL as M, alright, and if I were to bring this M outwards to the other side, so I would have M outside, so I would have this part, right? I would have M summation HK minus 1, right? So this part over here, if you think about it, is this part, M HK minus 1. So I actually put everything together like a Macam Muni. But anyway, and this comes the last part of this thing, where we are going to jump into another page, which is this one. Alright, your summation HK minus 1 over here, if you think about it, is come from where? Come from here. Where am I? Where's my pen? I will make a thicker one. Now this part over here, you see, it must be smaller than infinity. Alright, so this is a sufficient condition that you need to suffice. Alright, and next, your M, okay, is talking about your this thing over here. So your EL must be smaller or equals to M. So these are the two conditions, your bounded input, and this is your bounded output. Okay, so if I were to have HK minus L, I can also rewrite as HK only, because we don't care about the L anymore. To a certain extent, that's what they do, right? Anyway, so the summation of HK must be smaller than infinity. So at the total, you should say, or you should know that your transfer function, HK is your transfer function. Alright, the summation of all your H, alright, so you have H1 plus H2 plus H3 blah 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 all the way to H infinity, alright, must be smaller than infinity. So the summation of all the H must be smaller than infinity in order to be bounded output stable. Alright, bounded output stable. So in total, you have a BIBO input, BIBO output. So this thing is your output, this thing is your input. Your E to the power of L must be smaller or equals to M. And this symbol over here, this inverted A, tells you that for all of the EL, from E1, E2, E3, etc. to E infinity must be smaller than M. So in total, these are all the bounded input, bounded output. Next thing is, you may wonder why this part over here will becomes this part. Your HK minus L becomes HK. Alright, the next question you may ask. Alright, so in fact I have already proved to you the BIBO stability already. I just want to inform you that the reason behind why do we have HK minus L is equals to this, HKL. Alright, so if I want to prove to you, or over here H minus L, alright, so at first is this thing, HK minus L. I'll prove to you now that it is actually equals to this thing over here. Okay, so in order to prove, I will need a bounded input, alright, as 1. Okay, so if I have a bounded input as 1, okay, I'll have h. Let me see. I also don't know where it comes from, this transfer function. Seriously, your EL, alright, your input is equals to h minus L, alright, over the magnitude of h minus L. Ding ding. Right, I also don't know what the hell is going on. So I think that if you have an input of 1, alright, so in other words you have an input of 1, EL is equals to 1, you can also rewrite your 1 as h minus L over h minus L, right? And then if I were to magnitude this thing, if I were to say that this h minus L is equals to 0, alright, then 0 divided by everything is still equals to 0. Okay, so I think this is what it's trying to say over here, okay, over at this section. So if I were to prove that EL is equals to 0 when I have an input 1 to a certain weird extent of why do I do this, alright, then what? Then I can sub in UO is equals to this thing, E times your H, alright, EL H minus L. If you think about it, it's a bit different from what we have last stopped. We have EL HK minus L. Alright, now is EL H minus L. So I think they are not focused on any. So this UK previously was UK, and then we have this thing over here. Alright, now they actually ignore the UK, they just write it as U0. So in fact the output is, I think they just assume as 0, or I don't know. Alright, in the end, yeah, okay, sorry. This is only when the output, when U is equals to 0. Alright, so yeah, I was just, because if I were to clean things a little bit, you give me a while. Let's say if I were to copy this thing, alright, this is something that comes from just now. I rearrange, you got dirty no, I just rearrange and take the things that I need. If I were to just copy and paste it over here, alright, what they are doing it now over here is that if k is equals to 0, alright, then u0 must be equals or smaller. In this case we write as equals because there is still possibility that they are equal, right? So therefore summation, alright, from I should say that is L equals to minus infinity to infinity, alright, EL I'll just write as L first, okay, and then H is K, I put it as 0, right? So I have 0 minus L. So this is something like that. So this whole thing over here is being written over here. So it's EL, right? And then H minus L, because 0 minus L is minus L, right? So I have H minus L. Alright. So this is the initial condition of your output, so to speak lah. Okay? And next, if you were to sub in your EL as equals to this thing. Alright, so you have, instead of EL, I will have H minus L divided by H minus L. So I would have, if I were to zoom in a while, if I were to replace my EL as this dude, if I were to just paste it over here, okay? So H minus L times H minus L, what do I have? I have H minus L squared, right? So this thing over here is this thing, right? H minus L squared, this one, and H minus L, the magnitude of H minus L. So over here, the magnitude of H minus L is in fact H minus L. Okay, sorry. So if I were to cancel this, I will have H minus L. That's all. Ta-da! And in fact, I don't even know what I'm proving to you. But in fact, I'm just only proving to you that, well, hold on a while. That your HK minus L can be rewritten as HK. Okay? Given that what we have just proved to you. Alright? So at first you set your input as 1, and then your 1 can be represented by H minus L over H minus L. Alright, that's what they do lah. Alright, this should be H minus L. Okay, so the denominator they put it as a magnitude. Alright, so if H minus L they set it as equals to 0. So if your transfer function is equals to 0, for example, then the whole thing will be 0. And then next they just set their k equals to 0 from the definitions of this thing. Right? So they just set it as equals to 0. and then the rest of the k is equal to 0, and then you rearrange, you'll get eventually this thing. Alright, so unless your transfer function is lesser than infinity, alright, otherwise the system is not BIBO stable. So in order to have stability by any way, alright, you must have your transfer function to be smaller than infinity, while, alright, where all your EL, your input, must be smaller or equals to m. Okay, so these are all the boundary conditions you need to meet in order to be stable. I mean BIBO stable. Okay, so in the next video we'll do an example to strengthen this, although in fact we haven't proved anything about bounded input, bounded output, but we just write it in terms of initial notations, that's all. So anyway, so we'll do an example to just apply what we learned. Okay.